as we started to develop some very powerful formalism. But when you deal with formalisms, it's always very important not to get carried away with pure formulas. It's very important to see how it works in practice. And I will show you some powerful applications of this Hamiltonian formalism. So the idea of the Hamiltonian system was to recast dynamics in the form in which equations of motion are of the first order, and they are obtained from the principle of least action. So we said that we have the action, the most general action, which provide us, well, first of all, we introduced the notion of the phase space, which is 2n dimension, which is double dimension of the configuration space. And then in this phase space we wrote down the action in the form we noticed that actually the first term is parametric, is invariant under time reparametrization. Therefore, when we reparameterize time, the only contribution comes from this term, and so this function is conserved, and this is energy. This is called energy of the system. The simplest example of this construction is just the action of this type, which leads to the Hamilton equation when we vary it. The equation here, in general, are we said they can be written in two forms, either this form or we can invert this matrix. It's assumed F alpha beta, I remind you, was d alpha a beta minus d beta a alpha. When we invert this matrix, we get what is called the Poisson structure, well, Poisson brackets. Namely, we are able, we write down this in this form, where the brackets of any two functions, that's a very important notion, the Poisson brackets. If you have any two functions on the phase space, you define them by the you introduce the matrix E, which is the inverse of the matrix F, and you write it down as or you can say that just two coordinates in the phase space, their bracket is just E alpha beta y. And it's useful to remember the rule for dealing with a Poisson bracket is that you take B of y is dA dy alpha, dB dy beta, and y alpha y beta. The fundamental bracket definition is this, and this function, this tensor E, which is called, this is called symplectic structure. The inverse is the Poisson structure, and this function should satisfy. It should satisfy what is called the Jacobi identity. plus cycles is 0. Cycles mean that you take the term alpha, beta, gamma, then beta, gamma, alpha, then gamma, alpha, beta. You replace. So when you sum it together, it's 0. And this is, I will not be deriving this. Excuse me. This holds for any three functions on the phase space. This Jacobi identity. And the origin of the Jacobi identity is that the Poisson brackets are tightly connected with commutators. So far I'm just it's a powerful formalism and it takes some time to get used to it, but you will see a little later how it allows us to make general statements about very complicated systems, like systems of gas, for example, containing 10 to the 23 particles. We still are able to visualize this motion of particles, although there are 10 to the power of 23 of them. We will do it a little later. I just, at the moment, I just want to remind you the basic facts which we discussed last time. And one more thing. So we have this thing. There is one more important statement about this. By the way, this, of course, impose a strong condition on E, because y alpha, y beta, it's probably useful to write down. That's by definition of by this rule, we derive this relation, and then we write down the Jacobi identity. It boils to some highly non-trivial quadratic relation for this matrix E. For this, it's actually. Well, it's not easy to figure out how to solve it, but in fact, this Jacobi identity. So you take this combination, you add cyclic permutations, and it should be 0. But then when you think a little bit, you figure out where it comes from. Well, I will remember we had the similar cyclic identity for this F, which was quite trivial. When you have this relation, by the way, I also mentioned last time that A is analogous to vector potential in electrodynamics. While F is analogous to magnetic field. Do you remember what this relation was in terms of electrodynamic analogy? So let's suppose that A is just vector potential.
The divergence of the...
Yeah. It's a divergence of magnetic field equal to 0, the condition like that. And actually, if you also can interpret it, you can also consider this as if alpha and beta goes from 1 to 4, not from 1 to... If they go from 1 to 3, that's just magnetic field. If they go from 1 to 4, you have also terms of F alpha 4 and so on. They are interpreted as electric field. Actually, four-dimensional representation is for Maxwell theory is that it contains F alpha beta and F alpha 4. There are basic variables are three. It's anti-symmetric tensor, and alpha beta goes from 1 to 3. So you have three components of magnetic field and three components of electric field. Notice that when you want to ask them? Yeah, please.
I'm trying to E alpha beta is equal to F. Is that F inverse?
Yes, it's F inverse.
Okay.
And notice, by the way, that the number, or it's only in 3 dimensions, the number of components of electric field coincide with the number of components of magnetic field. Generally speaking, magnetic field is not a vector, but anyway, that's kind of clear. All right, so far I didn't say anything new in comparison. Let's now look at the Poisson brackets, and let's discuss the problem of symmetries and conservation laws in this context. It becomes much simpler than it was in our first approach, in the Lagrangian approach. It's become much simpler and much more transparent. Namely, we say that let's before we just looked at the symmetries which transform coordinate x. So let's return back to the simplest standard case in which we will always be checking ourselves. Namely, let's look at the phase space which contains P and X, which is splittable onto P and X. The non-splittable phase spaces we will discuss later. And let us ask the following question. Under what conditions the Hamiltonian structure remains the same? So let's consider the general transformation of coordinates. And let's ask under what circumstances the Hamilton equations preserve their form. For general, if you just take a general transformation, they will not preserve their form. It's all, I must, as a side remark, it's all looks powerful but complicated, the whole Hamiltonian mechanics and the whole issue of transformations and so on. And it is, in a sense. We should not forget that the best minds of 19th century, the great mathematicians like Hamilton, Lagrange, Euler, they worked very hard on this subject, and they transformed it in a very non-trivial and powerful apparatus. Okay, so what we need to ask, the question we need to ask is the following. We know from these relations, by the way, here it's quite obvious that if you call x as x1 and p as or y1 and p as y2, then the Poisson brackets y alpha, y beta is what is called anti-symmetric tensor, epsilon alpha beta, for which epsilon 1, 2 is 1, and epsilon 2, 1 is -1, and all other components are 0. That's, of course, very important thing, and it's trivially satisfy the Jacobi identity. And that's how it relates to this formalism. So now we want to find the condition in which, under which, so in original variables, p dot was equal to hp, and x dot was equal to hx. Now we change variables. What do we need to preserve this form? Probably with a new Hamiltonian. So what we need is that the Poisson brackets of new variable are equal to the Poisson brackets of old variables. So we want to, if this is true, then of course you simply have in the new variables the equations of motion will be h twiddle, p twiddle, and so on. So that we find we should now considering transformation of variables in the phase space, in 2n-dimensional space, and we are looking for transformations which preserve the Poisson structure or the Poisson bracket. Such transformations are called canonical, and they are very useful and important. Most useful transformations in Hamiltonian mechanics are canonical transformations. I would say I even can't remember any cases where non-canonical transformation where maybe there are some cases, I should think. But normally the transformations allowed in Hamiltonian mechanics is those canonical transformations. So let's calculate now. We have Px is df dp dg dx. And it should be, since Px is equal to 1, this also should be equal to 1. So we see that we have some non-trivial restriction on the function functions f and g. If generally the solution of this condition would depend on a single function, because there are two functions and one condition. But you probably can figure out what it means geometrically, this condition, this constraint. So let me explain a little bit. We have the phase space. And let's suppose that we have some domain in the phase space. When we make this transformation, this domain in new coordinate will be something different. And that's given by this. Now, this relation should tell you something about the image of this domain here. So this expression should be, you should remember something which you know from calculus. There are certain statements about of what kind of new domain could be.
Is this in Arnold as the thing that preserves volume?
Yes. Why it is preservation of volume? Why it is preservation of volume? Well, if you have general change of variables, let me remind you the following. I assume you know the following fact. Suppose we have some variables, and you change variables. Well, suppose you have one variable, and you integrate the integral over dy twiddle is df dy. So if you integrate any function, you can write it down as the fact that new differential is f prime of y, all differential. Or if you have a mapping, you take a certain link of the length dy, and when you make the map, it dilates or shrinks with a coefficient f prime. Is that familiar, this fact? I'm just going to ask you, suppose now we go to 2 dimensions. And you want to know what is the element of the here it was linear element of the length. Now it's a two-dimensional integral element of the surface. How to relate dy twiddle with dy's?
So
what's the generalization? This is basically the fundamental formula of calculus. Yeah. So, what is generalization of this formula for 2, 3, and 4, etc. dimensions? How? How you change variables? It's change of variables. So suppose you integrate some function here. I'm returning to this one-dimensional case. So you have some function, you have some integral, and what it says is that you can change, let's call them tilde. Let's now choose tilde as some function of y. As a result, this integral will be dy f prime of y psi of f of y. This is the formula which you definitely know in some form, right? And what I'm basically asking, what's the generalization of this formula when you have dy1, dy2, f, some arbitrary function psi of y1 and y2, and I now change variables. How to change variables in the multiple integral?
So you make a matrix constituting dy tilde I dyj.
That's correct. That's correct. The answer is, I shall write you the answer for you, and you will certainly recognize it. I assume that you shall recognize it. So we basically say that it's dy2 determinant dfi dyj psi of f1 f2. So instead of this f prime, you get the determinant which is called the Jacobian. Is that familiar? By the way, I will tell you a good mnemonic rule for finding such formulas. Very curious rule. So in one dimension, we simply change dy twiddle f prime of y dy. Now let's when you have several differentials, you have multiple integral, it's very convenient to imagine that it has geometrical reason that they are not usual numbers, that they are numbers which anti-commute. So let's assume that dy1, dy2 is equal to minus dy2, dy1, and dy1 square is 0. That's a digression from our main line, but I think it's, well, I thought you know this stuff. Anyway, now let's calculate this thing. We have d1 f1 dy1 plus d1 f2 d2 f1 dy2, and we have to multiply it, so we're now changing variables as if it's d1 f2 dy1 plus d2 f1 dy2. And now let's do multiplication, assuming that dy's, the differentials, anti-commute. There will be various terms. For example, there are 4 terms, as you see. So let's take the term which contain d1 f1, d1 f2, what it is equal to. I just can, I could avoid it, but I just can't resist showing you some beautiful tricks, which I love this stuff. You see dy1 square is 0, so this term will not enter. However, there will be term d1 f1, d2 f1, dy1, dy2. So let me, instead of saying it, let me write it. So it is equal to dy1 f1 d2 d2 f1 dy1 dy2 plus d2 f1 d1 f2, actually it's 2 here, dy2 dy1. And when you take into account that this is equal to minus this, it's equal to d1 f, it's equal to the determinant di fj dy1 dy2. And that's a general prescription. You will get, when you have a multi-dimensional space, dy1 dy2 is the element of two-dimensional surface, but there could be some elements of higher dimensional surface and so on. And for all of them, this prescription, treat differentials as anti-commuting, it works. The geometrical meaning of this is that when you have a small parallelogram, you introduce orientation. There are its area is the vector product of these two vectors, and it depends on how you orient your parallelogram. but I should not go. We can spend all course discussing geometry, and that's not my goal. Still, you should remember that this is the thing. And now I'm returning to my question, which I didn't think that it will lead to this long discussion, but anyway. What is written here? What kind of, how it relates to what we just discussed?
Is that determinant?
It is a determinant. And so what it says that under canonical transformation, the domain changes. So you should imagine it this way. We can always say that the boundary of the domain is some parametrized curve. And now we make this, well, that's the original. And now we make the transformation, we get a different curve, which is written here. And so what it tells us that the volume of the original domain is the same as the volume of the finite domain. The point is that when we have only two variables, that's, by the way, not a general statement. It refers only to two-dimensional phase space. In higher dimensional phase space, canonicity of transformation is a, well, it's, I shall explain it to you what it is. But in two dimensions, it's just that we make that deformation which preserves the area of the domains. That's the geometrical meaning of the condition of preservation of the Poisson brackets. When we have, it's actually quite obvious that when you have multiple, many multidimensional phase space, it's not that simple. In multidimensional phase space, pi xj is Kronecker delta ij, and so you have much more conditions when you write down that this is equal to so you can ask how to find the general canonical transformation. Well, I first have to explain how to, or why we're so interested in this canonical. After we understand the meaning of canonicity, we will be able to solve problems with it. Well, you see, first of all, let's consider the condition. I have to do it a little more of this. Let's consider the condition that p tilde is, let's consider infinitesimal canonical transformation. Then we have the following condition. So we have to write down the condition that dp I just want to keep my notations. Dp over dp dx over dx minus dp dx dx dp. Let's substitute this and have it and just expand in delta p and delta x, we will get d delta p over dp plus d delta x over dx is equal to 0. This can be easily solved by choosing delta p in this form. Delta p will be it's convenient for me to define it this way. It's obvious that when you do it this way, and I will explain it, that this will be satisfied. So it's easy to see that this is in the multidimensional phase space. The most general canonical transformation is delta pi is minus df dxi delta xi and canonical transformations are generated infinitesimally by the function f of p and x. So you have one arbitrary function, and it is not surprising that we ended up with one arbitrary function. Here we have two arbitrary functions with one constraint, so it's clear that they must lead to one arbitrary function. Okay, but now I have these equations should tell you something. So you can take arbitrary f and find this equation. First of all, they should remind you something. Think of the Hamiltonian equation themselves. What is similar to this relation? I remind you the Hamilton equation which we derived in this P space, where pi dot that's the Hamilton equations, and now I want you to compare these canonical transformations with the equations themselves. What is similar here? Well, you should see that here we see how the functions change in time. Here we have basically the same equation with f being some kind of a Hamiltonian, which tells you another transformation in time. So what it tells you, what should be obvious, is that that the Hamiltonian development is performing canonical transformations on p and x. What I mean by that? I mean, let's take pi 0 xi 0 and consider pi of t as a function pi 0 xi 0. If we consider t infinitesimal, we just get the canonical transformation generated by h. So that's a bit formal and complicated. We will have a rest with concrete problem in a moment, but I have to finish this those things. But now, when you let's sum up and derive something non-trivial from here. So we have these relations which are just the Poisson bracket relations. And we have the infinitesimal transformation which preserve the Poisson brackets. Okay. Now let's suppose that the Hamiltonian is invariant. We didn't yet we consider some canonical transformation, but we now assume that the Hamiltonian has symmetry. So let's suppose that the Hamiltonian doesn't change for some particular transformation. For infinitesimal transformation, we have that's for general transformation. Okay, and so delta H, which is the difference of these two, is can be written down as the change of the Hamiltonian is equal to df dpi dh dxi minus df dxi dh dpi. And if we have symmetry, then this will be 0. And now that's by definition of symmetry, that we have canonical transformation, and then that's a thing. Now I want you to think a little bit and figure out it actually Netter's theorem, the relation between integrals of motion and symmetries become completely trivial in this language. After we suffered enough to develop the language, the interesting statements in this language become completely obvious. So why is that? Why I'm saying that? Why this relation, which is just symmetry statement, simultaneously means that that we have integral of motion related to the conserved quantity related to this. Yeah, because compare this. This was symmetry statement. Now let's take f of p and x, which depend on p of t and x of t, and consider its time derivative. Its time derivative is the Poisson bracket, but this Poisson bracket is 0. So we immediately say it's becomes completely trivial that if you have an arbitrary canonical transformation which leaves Hamiltonian unchanged, then this generating function of this canonical transformation, this is the generating function, is conserved quantity, doesn't change with time. You don't have to calculate anything else. And it's an extension of Netter's theorem, because before we looked at the transformation which did not depend on momenta. We looked at the but now we have this extended, much more general transformations which contain one arbitrary function. Each transformation is defined by an arbitrary function on the 2n-dimensional space or 6n-dimensional space. And we will use it now. And I probably don't have time now already, but for explaining this, well, okay. Let's do some exercises with what we learned. first of all, we learned various forms. We are changing the forms in which we recast the ordinary Newton equation. We change the form of the variational principle. The variational principle turns out to be related to the phase space and so on. So let's apply this knowledge which we acquired. First, I will give you two, since you suffered enough through these formal derivations, I will give you two beautiful physical examples of how it works. One is the motion of planets. We derived the variational principle. The action which we looked at was, and that was the Hamilton principle, from which we derived the Hamilton equation. But we can also, if delta S is 0 for any variation of p and x, it will also be 0 for the variation of p and x which preserves symmetry. So consider only p and x for which h of p and x is equal to energy and is a constant. Then we have a possible variational principle called Maupertuis principle, which I mentioned, which is, generally speaking, it's the statement that this integral is invariant under transformation. And a small trick which we will need to describe planets, it turns out to be much more, since p and x are quite symmetric, you can, it doesn't matter really what you call p, what you call x. Another principle which also holds is that now let's see how this principle works. We will be we consider the center and a planet which moves around the center, and of course p squared divided by 2m minus the constant divided by r is the energy. And we will, since we want the closed, we are interested now at the closed orbits, the energy should be negative, and it should be equal to minus epsilon. Now, it's easy to see that when this thing moves, dp and dx are parallel. So we say that the variational principle we should use is this one. Okay, and now what is r? And r should be expressed in terms of p. Okay, now let's do this. R is, let's see, we have p squared divided by 2m plus epsilon is equal to c divided by r. And so when I change the scales and change the units, I said take mass equal 1/2. R will be proportional 1 divided by p squared plus epsilon. So far nothing spectacular is happening, but now we have a variational principle. It should be interpreted now without this thing. If we didn't have the denominator here, what this variational principle would say. Suppose I don't denominator is absent. Then what is the statement then? Excuse me? Not why. You see, you have a curve P of S, and that's just the condition that the P of S is such that this expression is a minimum. So it's in the momentum space now. We have a straight line, P of S without this thing. So, but with this thing, it looks a bit, so we derived p squared plus epsilon dpds. I'm just rewriting the same formula. Of course, we can start variation and can write down the Euler-Lagrange equation and describe the motion in the momentum space. But we will not do this. We will find the answer geometrically.
Sorry, a quick question. How was the 2m lost?
Oh, 2m lost in my usual way. I set m equal to 1/2.
Okay.
It's just irrelevant. But what's relevant is this. And we have to, to appreciate this expression, I have to add some geometrical information, which you will we will give you problems. One of them will be the checking of this statement. So let's consider a sphere. Let's keep it in mind, but at the moment it's a pure, let's compare it with a purely geometrical problem. You have a sphere and there's a plane here which touches at the South Pole. And as I assume you know, you can map a sphere, two-dimensional sphere on two-dimensional plane by associating each point. You take the North Pole. If this point goes to this point goes to this point. Do you know what this construction? What is it? It's stereographic projection. It's what is called stereographic projection. You just project sphere on the plane. Or you can also derive it in the following way. You have the sphere, the two-dimensional sphere is defined by this equation. I will take the unit sphere, okay? Interrupt me if something is unclear, because the whole thing is crystal clear. What could be unclear is just notations or my words or something, but not the subject. So this is the equation which defines the sphere in three-dimensional space. Just without it, it would be a circle. Actually, you can work on a circle as well. You can stereographically project the circle in the same way. And you can parameterize in various ways this thing. You can just the parameterization which is convenient, stereographic parameterization of those pi things. That will be, you will check in your home exercise. And 3, this is the formula for stereographic projection. So for a given n is this unit vector which defines the sphere. You see, for arbitrary x, if you take sum of 3 squares, you will get 1. You will get, well, that's pretty obvious. And you also will check it. Now, let's consider a distance element on a sphere. The distance on a sphere will be simply the square of the distance between two neighboring points will be dn square, which again that will be the calculations which you will do. This is a standard geometric calculation, but you will do it in your homework. You will get dx square. Just trust me on that you have to differentiate these things and sum square. You can also write down it, by the way, using it's the same thing as writing it down with polar and azimuthal angles. D theta square plus sine square theta d phi square. That's maybe more familiar form of the element of length on the sphere. So far there's nothing. It's just some elementary geometry. It's nothing deep here. And you'll find the distance between 2 points. And now tell me why I claim that even if you don't see it yet, the problem is solved. Our mechanical problem is solved. Why I'm saying this? After you convince yourself that this is the distance on a sphere. Try to see the relation between these geometrical things and this is geometry, how it is related to our variational principle. It's very important to train yourself to see connections between apparently different things. And even if you go ahead, please.
Because if you take the square root, you get ds equals dx equals 1 plus x squared, and then you can put in p instead of f.
Yes, that's exactly, you are right. This variational problem is simply the problem of minimal distance on a sphere. That's the point. It's just simply minimal distance on a sphere. But we know the answer. We don't have to solve differential equation. Of course, you can derive everything by following variational calculus, writing down differential equations, solving them, etc. No need of that. You know the answer. What is the answer for the geodesic on a sphere? Big circles. Big circles. So now we can answer the following question. The first question which we can answer is this. Suppose we have a planet moving around the sun. Why the trajectory is closed? If you have, generally speaking, you would expect that trajectory is not closing. Trajectory of the planet, it will return, but it missed this point, and it's missed this point again, and so on. It will be something complicated. In fact, we know that the planets move along their closed trajectories. Fortunately for us, otherwise the weather will be terrible. Okay, why is that?
Because the great circle is closed.
Because great circle is closed. If you take, remember how we derive it. If we derive it from here, if we take some different power here, for instance, say 1 and 1/2 or whatever, it will be a totally different figure. You still can interpret this expression as a minimal distance on some manifold, but generally geodesics are not closed. It's a miracle that geodesic is closed. If you deform the sphere, if you deform the potential, for instance, you deform the sphere, and the geodesic will not be closed anymore. It's only for strictly Newton force that geodesic is closed. And it's actually kind of interesting that you see Kepler started with the assumption that trajectories of planets are strict circles, and he worked for quite a while thinking that this is the case. And for him it was extremely important statement because he thought that the circles are the most perfect figures, and so he really wanted the planet to move along the circle, and it was a great disappointment which he described. He wrote very well, actually. I recommend you to read some of his not papers, but he wrote some articles about various things. For example, about snowflakes or etc. In very good style. Anyway, it was a great disappointment for him to find that there are ellipses which are not perfect circles. But in a sense, he is vindicated because in the momentum space there are strict circles. So when they tell you that planets move along ellipses, don't believe it. All right. So you see, that's a nice way to. This allows us to move to think globally. It also tells us that there is this particular interaction, this particular Hamiltonian has some extra non-trivial symmetry because on a sphere we have symmetry. All points of a sphere are equivalent, so rotation of a sphere is a symmetry, and this is a symmetry totally different from rotation in space. So in a sense, in the Newton problem with 1 over r potential, we have two things. We have symmetry of rotation of space, which leads to what conservation law? It's angular momentum, and angular momentum is responsible for the orbits to lie in the plane. We have angular momentum perpendicular to the plane. It's conserved, so the plane is not changing. That's an easy part. But there's also symmetry under rotation in the momentum space. And that leads to a new integral, kind of a, you can write it down. People, of course, wrote it down. It's called Runge-Lenz vector. And it played, believe it or not, extremely important role in solving quantum mechanical. It was Pauli who solved the problem for hydrogen atom in quantum mechanics, and he solved it by using this Runge-Lenz vector. Incidentally, without any suspicion of this geometrical meaning. People didn't understand for a long time the geometrical meaning of the Runge-Lenz vector. It was just a formal derivation, formal observation that certain expression is conserved in this case. We will return actually to the cases when you have some unexpected integrals of motion, to the case of what is called completely integrable systems, where apart from the standard integral of motion like energy, angular momentum, etc., you have also something quite unexpected. All right, the calculation you will do at home here. Let me now give you another example. I will still have time, I guess, for this, of the power of the Hamiltonian formalism. For me, actually, this type of things is just an example of, this is more or less by definition of what is called the beauty of theoretical physics, when you somehow the ideas from the totally different subjects melt together and give some powerful result without complicated calculations. Well, there is another thing, which is another statement which is extremely counterintuitive at first, but it follows from our Hamiltonian formalism immediately. The statement will be the following. What we are discussing now is a theorem called Poincaré recurrence theorem. And the statement is basically the following. When you formulate it, it looks like an incredibly difficult theorem. At the same time, the proof takes a few lines. So let's take a box with black balls here, moving with arbitrary velocities, white balls here. Then we remove the separation, and they move arbitrarily. It's clear that intuition tells us that they will mix up, and there will be more or less equal number, equal probability to find a black ball and a white ball. Not quite so. Well, this is correct in a sense. However, the theorem by Poincaré tells you that if you wait very long, you will return very close, arbitrarily close to the initial configuration. There will be a recurrence. And we will prove this in a few lines using the Hamiltonians. Well, it led to wrong conclusions, but the theorem is right. Poincaré actually was led to. For him, this theorem meant that statistical mechanics of Boltzmann is no good, but it was a mistake. Okay, how we prove it? First of all, we notice that we already noticed that when we have a domain in the phase space, it develops with time. It is, of course, when I draw this picture, it's my way of depicting the space with dimension 10 to the 23. So just imagine how many x's there are, in fact. When it moves, it performs canonical transformation, and as we said, the volume of this domain should not change. So if this is the picture t equals 0 and this is the picture t equals 1, these volumes are the same. Okay, now let's begin with certain domain, and we have the transformations from time 0, time 1, and so on. And let's suppose that there is a certain domain inside our set. Let's call this set A0, which will never return back, which move, which will never return to the original position inside this original domain. So in other words, if I at the time 1, I will get the set A1, which I will denote as denote transformation by T, A0, and by the assumption that it will never return, we say that TA0, its intersection with A0 is equal to 0. Now, probably I should have said what I'm driving at. I was driving at the statement that I will be making the assumption that there is a certain domain which will never return back, but it will lead us to a contradiction. That was how Poincaré proved it. So now take this set A1 and consider T square of A1. And once again, it will its intersection with A0 must be 0. As a result of this thing, of this construction, we'll get domains A1, A2, etc. All of them not intersecting. So AI, AJ is 0. And all of them have the same volume. So the volume of A0 is equal to the volume of A1, and so on. Now let's consider the phase space, which we are considering. It has finite volume, namely in the x direction. There is a finite volume because P and X, both P and X of these particles are bounded. Why X is bounded? We have a box. Why P is bounded? Conservation of energy, exactly. So we come to a paradox that we have infinite number of domains of non-intersecting domain with infinite volume, and we cannot place it into the original finite volume of the phase space. And therefore, the only conclusion you can draw from this is that when you have any domain of finite volume, after some time it will return to its original position, to the original domain A0. It will be a part of the original domain A0. So, which in terms of, here we are talking about, notice what we are doing is that we replaced the motion of 10 to the 23 particles by the motion of a single particle, but in multidimensional space. And we can use geometrical intuition to some extent even in this space. Here it's not even geometrical intuition, it's much very crude fact that you basically, it must return because the volume is preserved. And if it doesn't return, you will put it here, here, here. So finally there will be no place for this domain. And now this theorem is obviously contradicting the statement of statistical mechanics that after some time, those balls or molecules must mix up, and that was there was quite dramatic controversy when this theorem was discovered. There was another mathematician, Zermelo, which attacked Boltzmann and said that it's incorrect. The idea was that you, in principle, cannot derive statistical mechanics from the usual mechanics, and that was of course, very bitter discussion, because Boltzmann was doing this derivation all his life. It was his life work. Anyway, the resolution, we will discuss statistical mechanics maybe even next time, maybe a couple of lectures after that. The resolution of this paradox is, as in case in many paradoxes in physics, even in modern times, even paradoxes that people are discussing today, they are no better than in connection with black holes. People are examining various paradoxes, being that was basically on the same level as these guys were discussing statistical mechanics. So the resolution here, anyway, the resolution here is that the time which it takes for recurrence is of the order of e to the number of particles. That can be, that's not quite trivial to prove, but it can be proved. As a result, if you tend n to infinity first, then recurrence theorem does not apply, and indeed Boltzmann picture arises. If you take t to infinity first at finite n, then you will get recurrences, but that's not a physical limit. The physical limit, obviously, it will require time much greater than the life of the universe. So, which is a little too long to wait. So that's how it's resolved. But we will return to there are still. It's kind of interesting that now, almost 200 years or 100 years after, there is still some discussion of time reversal in statistical mechanics and its compatibility with microscopic dynamics and so on. Okay, and that was just to show you how it's kind of quite unexpected. The proof is really one-liner, and the theorem looks quite majestic, I would say. Very interesting. Okay, let me stop here.